The first thing I want to kind of ask you, now everything's written here so that helps, you can cheat. But when I say the word field, what do you think of? And it can be anything, it doesn't have to even do with physics or science, just a quick poll. What do you think of when I say field?
Just the word field, I think like a field of grass, to be honest.
Field of grass, perfect. What do you think of when I say the word field? We're doing a Freudian association here, real quick.
Same thing.
You think of the field of grass. Field.
Like a career field.
A career, what you're going to do. Field. Grass. Field.
Just an area.
An area. Field.
Soccer.
Soccer. Field.
Like a field of study.
A field of study. Field.
Space.
Space. Okay. So you can see it's not really one we're used to being common sort of parlance the way we do in physics. But in physics, when I say field, you want to translate that in your head to force. A field allows you to keep track of the force everywhere in space, almost always due to one of three things: a charge, a mass, or a current. If it's the field from a charge, we call it the electric field, because it's going to tell us about the forces on other charges. So if I have a positive charge here, it makes a field everywhere in space that allows me to know, no matter where I put another charge, what will the force on it be. And if it's a positive charge here and I put a negative charge here, then I know I get an attractive force. If I put another positive charge, I know it's a repulsive force. Mass generates gravitational fields. That tells me if I have a massive object, say the Earth, when I know its gravitational field, I know the force on any other massive object no matter where I put it. Common way to think about, for instance, the sun has its gravitational field that I use to figure out the force on the Earth. The Earth has its gravitational field that I use to figure out the force on you, me, the moon, cars, planes. Okay? So field is a language for force. Currents, and this is the tricky one, currents are what create magnetic fields. And currents are moving charges. And so likewise, remember, it goes both ways. Magnetic fields therefore make their forces on moving charges. Gravitational fields act on things with mass. Electric fields act on things with charge. So it's kind of a two-way street here. That's the connection. So the field is associated with the object that's going to generate the force. I put it in quotes. And then when you stick another object out there, that field tells you the force on it. So again, when you hear field, you think forces. When we hear potential or potential energy, we think energy. And with electricity, the other word we use for that is voltage. So when you hear voltage in everyday usage, so like there's so many volts for this circuit, or so many volts in the wall, or so many volt AC, or your battery generates 9 volts, or it's a 1.5 volt battery, or whatever the battery is, or a 12 volt battery, when we hear volt, we're talking energy. And when we want to think about things moving, we can either use a force picture or an energy picture. If I have an electric field and I stick a conductor in it, conductors are things that have charges that are free to move. When they feel a force, they'll move, and I get a current. If I have a voltage across a conductor, that means there's an energy difference between one end and the other, just like the gravitational potential energy of my pen being up here versus down here. And so when I put a voltage, I get a current. So typically when we talk about currents, we're going to talk about voltages. It's easier to think in the energy picture than the force picture. That's just the common thing. So that's why you talk about the voltage potential in your neurons, the voltage potential in batteries, and all of the electricity has to do with voltages. Getting this language down is actually very useful because so much of our world is based on electricity and magnetism these days. Understanding safety, understanding health, understanding what's really going to hurt you and what's not really comes down a lot to understanding these language issues. The next big language issue is understanding our language regarding radiation. And by this I mean electromagnetic radiation. And this is where it's key to understand that fields are actually real things. They're just not a trick for keeping track of the force, because light and all electromagnetic radiation is an oscillating electric and magnetic field. It actually is a field that oscillates back and forth and travels through space. And if I think about it, oh, I'm going to cover that up quickly. Name some types of electromagnetic radiation.
Like microwave.
Microwaves. What else? The big one. We're all using it right now.
Light.
Light. Okay. What else? UV. What else? Infrared. What else? Anyone listen to the radio anymore? Radio waves. Anyone ever get an X-ray? X-rays. Okay? And why do I put them in this order? There are really two energy sort of tables you want to remember. Last week we did gas, liquid, solid. Which had the higher energy? Quick review.
Yeah.
Gas. Electromagnetic radiation, same thing. Radio waves, lowest energy. X-ray, highest energy. One of the key things about radiation is it comes in what we call discrete energy packets, photons. You want to think of them as little packets of energy. And when they interact with matter, it's what that little packet of energy is that determines if anything happens. And this is where radiation safety and knowing what it does to your body is key. X-rays have a high enough packet of energy that they tend to do what? Why does the doctor leave the room when the X-ray machine is turned on? And why do they put a big lead vest on you? So it doesn't harm you. And how does X-rays harm you?
Does it heat up your inside?
It's not heat. It actually breaks chemical bonds. And if it breaks DNA, that's genetic mutations. That's bad. Okay, so you can get real damage. UV, what does UV tend to do to you?
Like burst your skin.
So if you're lucky and it's nice, it makes you nice and tan. If you're unlucky and you've got fair Irish skin like me, it burns you, right? Again, it has the right energy to have a chemical reaction with your skin, to cause a reaction in your skin that causes either tanning or burning because it matches the molecules. Visible light, does it tend to do you any damage? No, because it has the wrong energy to interact with any of your molecules except the ones in your eyes that allow you to see. Microwave/infrared, what is that very useful for? Heating things. And that works because the main vibration mode of water does a really good job of absorbing microwaves. And so if I think about it, if I increase the energy of a molecule, I've increased its what? Temperature, because temperature measures energy. So that's how I heat things up. Radio waves tend to do nothing to you because they're, again, such a low energy, they don't really interact with anything in you. Okay? So this is, and it's interacting because it's an electric and magnetic field, so it interacts with the charges, the electrons in your matter, because we said electric fields interact with charges. The electrons in your body are also moving, so they're little mini currents, so the magnetic field part can interact with the current. It's mostly the electric field in it that interacts, but they both can in principle. The final two big ideas from this section that are kind of newer, I think, to most people have to do with how materials respond. So when I have an electric field, when I'm trying to make forces from charges, what matters is whether I have a conductor or an insulator. The basic idea is in conductors, there's a bunch of electrons that are free to move. So if I apply an electric field, it can make a force on the electrons because they're charged particles. They're free to move. That moving makes a current. The other really cool thing about conductors is those charges can move around, and they always move around in such a way so that the electric field inside the conductor is zero. So one demo I can't do because we don't have it, but you can either look it up on YouTube or go to a science museum. Have you ever seen the guy or woman stand in a metal cage and then they shoot lightning bolts at him? Or did you see, what was the movie, Sorcerer's Apprentice? Because he stands inside the cage and they shoot big lightning bolts at him. And it works because the electric field can't get inside the metal cage, so you're safe. It's the same reason why when cars used to be made out of metal, you were safest in a car in a lightning storm. Now that they're made out of fiberglass, I'm not sure how well they work. Insulators, the charges are fixed. So you apply a voltage, they can't move, you don't get a current. If you apply a big enough voltage, right? It's just an energy question, right? Voltage is energy. If we think about it that way, I can rip the charges off, and that's where I get basically lightning in the air. There's basically an insulator, but lightning is ripping the charges off the air molecules. Magnetic fields are much more complicated. We're mostly going to do this as we go through the demos. Basically, remember, currents make magnetic fields. So magnetic fields interact with currents. So if you have a metal, there are three basically types of metals. Those where there's no organized currents in any way, so the magnetic field does not interact with it and you get no force. Those which are paramagnetic or ferromagnetic, where that's a refrigerator, right? You stick your magnet in the refrigerator, it attracts. Why? Because the magnetic field in the magnet organizes the currents in the material that makes a magnetic field that's in the same direction, which means the north and south poles are near each other, and I get attraction. Diamagnetic materials are kind of cool because they organize the magnetic fields in such a way that it's opposite, and you get repulsion. And we're going to see some examples of these. But this is the really tricky piece, and it's what makes all of technology, it's not really at the heart of all of our technology, is if I can make my magnetic field change in time, maybe by the current changing or moving the magnet, then I actually get an electric field that's changing. If I have an electric field, I don't need a current around, right? I just need a charge around. So if I have a conductor, that electric field will make the current flow. That current, which is changing in time, makes its own magnetic field, because currents make magnetic fields. And this magnetic field opposes that magnetic field, and I get a repulsive force. So we're going to see these in the demos.